Now in our next example, we're going to look at this question of combining our functions from a slightly different perspective. We're going to evaluate our functions now at inputs. So if we would like to know what f plus g of 3 is, we could use the definition which says that f plus g of anything is f of that value plus g of that value. And now we know that f takes 2 times 3 minus 1, and g of 3 is going to be negative 3 plus 2. So our result, if we multiply 2 times 3, we get 6 minus 1, so 5. And negative 3 plus 2 would be negative 1. So 5 minus 1, 4 would be our final answer. So that's one way we could handle the situation. And it's perfectly viable to do things that way. But another way to look at it would be to plug 3 into the function that we found, the function f plus g. So remember that f plus g of x is x plus 1. Alright? So with that in mind, f plus g of 3 is going to be the result of plugging 3 into this function. So notice how much quicker that was. When we built the function that did what we wanted in advance, then we could plug in our x value very quickly, figure out what the result would be. This is a nice way of doing things when you're going to be using a combination like this often. If you find that you're using a combination like f plus g or cost minus revenue, for instance, you may want to plug something into the difference function or the addition or the sum function over and over again. And it gets quite tedious plugging a value into 2 functions and then calculating the sum of the results, when you could simply find that sum function and plug your input directly into that. So let's look at another of this type of question. One way we could handle this would be to think of the definition, which says this is equal to g of 1 minus f of 1, which would be g would be negative 1 plus 2, and we are subtracting f of 1, which would be 2 times 1 minus 1. Okay, so that's 1 minus 2 times 1 minus 1 would be 1 also, the result being 0. However, recall that the difference function g minus f of x is given by negative 3x plus 3. So we could also calculate g minus f of 1 by plugging 1 into this function. And that's negative 3 plus 3, which is 0. So I would argue that this process is much quicker if you already know what that function is. Now it might be quicker in a one-time scenario to simply evaluate both functions at your input and find the difference or sum or product or whatever you're interested in. But if you're doing this frequently, if you're using the difference of these 2 functions a lot, it's probably easier to find that function and use it instead. Alright, we'll look at one more. F times g of 0. We could think of that as f of 0 times g of 0, again referring back to that first definition in this section. Now f of 0, that would be 2 times 0 minus 1, and we're going to multiply that by g of 0, which is negative 0 plus 2. It's a little weird looking, but 2 times 0 is 0. So 0 minus 1, and we're multiplying that by negative 0 plus 2. I think that's going to be positive 2. So negative 1 times positive 2 gives us negative 2. Alright, if you refer back to where we just were in the previous example, recall that f times g of x is equal to negative 2x squared plus 5x minus 2. So if we plug 0 into that, that would be negative 2 times 0 squared plus 5 times 0 minus 2. Well, negative 2 times 0 squared is 0. 5 times 0 is 0, so we just end up with negative 2. So quick and easy to use those functions that you've already got. Now in our next example, we are going to be somewhat limited. Here we're given two functions, f and g, but we're not given formulas for those functions. We're given tables. So in this case, it would be very difficult for me to figure out a function for f plus g, or f minus g, or f times g, or any of those combinations that we've seen so far. I don't know what the formulas are, so I can't plug those formulas in as we did in the first example. So what I need to rely on instead in this case is those definitions. So f plus g of 4, I can think of that. I don't know what the function f plus g is, so I'm going to have to think of this as f of 4 plus g of 4. Now I have tables to tell me exactly what f of 4 would be. F of 4, 4 being our input, results in an output of 2. And g of 4, over here on my g table, if 4 is my input in g, 9 is the output. So our result is 11. Alright, so that's how we're going to have to handle all of these. F times g, again, I don't have a function that'll calculate f times g of an input, but I can calculate f of that input and multiply the result by g of that input. Well, f of 0 is 0. G of 0 is negative 3. Well, 0 times anything still gives us 0. Okay. Now, f over g, that means we want to take that input, plug it into f, and divide that by the result of plugging it into g. So I need to know what f of 2 is, and I need to know what g of 2 is. Well, f of 2 is undefined. 2 is not a valid input in this function f. Well, we can't plug stuff into this combination function that we can't plug into the component functions. On the other hand, f over g of 1, well, we can figure out what f of 1 is, and we can figure out what g of 1 is. Both of those are defined. Now, f of 1 gives us an output of 1, and g of 1 gives us an output of 0. Well, this is a problem. We're not allowed to have 0 in the denominator, so this is also undefined. Remember how this function f over g, if we go back to the original problem where we saw this type of thing, we want to make sure that g is never 0. Well, g is 0 when x is 1. So x cannot be 1 for this function. And here we're trying to plug in 1 and we get something nonsensical. We're dividing by 0, which is not allowed. So let's try one more of those. Let's do, how about f over g of 4? Okay, well, we'll figure out what f of 4 is and divide that by whatever g of 4 is. And as we saw in part A, f of 4 is 2, and g of 4 is 9. So those are our components and our quotient. The result would be 2 over 9. All right, now you can do the same type of thing if the presentation of your functions is as graphs. If, for instance, we had graphs, we could also elucidate all of this information that we are using to arrive at our final answer. We'll see a little bit of that a little later on. For now, we're going to move on from these combinations, although before I do, I would like to remind you that we have seen this before. Remember the profit functions? We found those by calculating revenue minus cost. So we could think of our profit function as R minus C functions. So we're sort of extending that notation to the notation that we are seeing in this section. This is how we might think of the profit function, the difference function between the revenue and the cost. All right. I'd like to shift gears a little bit and look at composition of functions. The notes for this are on the next page of this section. And I'd just like to jot that down. So we're going to be dealing with something that looks like f. Little circle means we are composing f with g. So f composed with g of x. What this means is we're going to take g of x and plug that into the function f. Okay? So you can think of plugging x into g and then plugging the result into f. And I like to think of this as f of g of x. Alright, so here we'll see a couple of different ways that we can use this. Here we've got three functions, f of x, g of x, and h of x. And first we're going to look at how this composition f of g of x will look. Well, remember the definition up here says we're going to take the second function and plug it into the first function. So we're looking for f of g of x. Alright, so there are a couple of ways we can handle this, and I'll show you both ways. F of g of x means we're going to plug the whole function g into the function f. So we can think of f as taking its input and multiplying it by 3 and adding 1. So we could think of this as 3 times our input, g of x, plus 1. And then we can figure that g of x is equivalent or equal to x squared minus 1. So we can make that replacement. And we're still multiplying by 3, and we're still adding 1. So this is 3x squared minus 3. Remember, we have to distribute that 3, plus 1. So we get 3x squared minus 2. Alright. Now the other way of thinking of it is basically the same idea, but in a slightly different order. So remember, f of g of x, well, we know what g of x is. This is f of x squared minus 1. Okay, so that's what we need to plug into our function f. And what happens when we do that? We get 3 times x squared minus 1 plus 2. So we're plugging that value in for x. And we can simplify in the same way. Distribute the 3. We get 3x squared minus 3 plus 2. And we end up in the same place. 3x squared. Sorry, that should be a 1. F is 3 times the input plus 1. Should be a 1. So we end up in the same place now. 3x squared minus 2. Alright, let's try one more of those. Let's look at the other direction. If we ask about g of f of x, what are we asking for? Well, we're saying take f and plug it into g. Okay. Well, we know what f of x is. This is asking us for g of 3x plus 1. And what does g do? Well, g takes its input and squares it and subtracts 1. So we're going to take this input, 3x plus 1, and we're squaring it, and then we'll subtract 1. So we could stop there, but we might as well simplify. This is 3x plus 1, 3x plus 1, minus 1. So that's 9x squared. 3x and 3x gives us 6x plus 1 minus 1. And our 1's cancel, and we're left with 9x squared plus 6x. So notice that these functions that we came up with are very different. They're both quadratics, but they're completely different quadratics. All of our coefficients are different. So it matters which order your composition is going. Let's look at one more of those. So how about we bring h into the mix? Let's find f of h of x. Well, which function are we plugging into which? F is getting h plugged into it. So f of h of x would be f of the expression 1 over x plus 2. So that's, well, what does f do with its inputs? We're going to multiply the input by 3, and we're going to add 1. And we could stop right there. That's far enough. Now you could also continue and simplify this a little. Just multiply in the 3. That's 3 over x plus 2 plus 1. We could get a common denominator, multiply the 1 by x plus 2 over x plus 2, and then add, so 3 over x plus 2 plus x plus 2 over x plus 2. Our final result being 3 plus 2, 5, and x in the numerator, all over x plus 2. Now, one interesting thing to discuss is what is the domain going to look like for our final function? Well, when we're composing functions, what are we trying to accomplish? The function that we end up with does the job of plugging an input into the inner function and the result into the outer function. So let's look at an example of actual values to see what we mean by that. Alright, now just like before, we can apply the definition, or we can use the functions that we have already found. So one way to think of this is f composed with g is asking us to plug g into f. Now this time we're plugging 2 into the function we come up with. So we're plugging 2 into g into f. So we can do a little bit of side work. Notice that g of 2 is 2 squared minus 1. That's 4 minus 1, 3. So that's what we're actually plugging into f. Now f of 3 is equal to 3 times 3 plus 1. That's 9 plus 1, that's 10. So here we manually had to plug 2 into G, calculate the result, plug that result into f, and then calculate the result of that. But we have a function, f composed with g, which we calculated in the previous problem, and that was 3x squared minus 2. So what this function should do for us, if we plug 2 into it, is output 10. Accomplish the same result as when we did the manual process. So f composed with g, our function name, of 2 would be 3 times 2 squared minus 2. Well, 3 times 2 squared, we'll square the 2, that's 3 times 4 minus 2, that's 12 minus 2, and the result is the same. We get 10 in both cases. And that's not a coincidence. That's because this function does this whole process for us. So, behind the scenes, we've already done those calculations, we've simplified and created a formula that distilled down this idea, and whenever we plug an input into this function, we'll achieve the same end as if we plugged the input into G, then the result into F. So I'd like to look at one more example of this process with these functions. So f of h of negative 2, what's that asking for? F of h of negative 2. Okay, so we need to figure out what is h of negative 2, so that would be plugging negative 2 into our formula for h. So negative 2 plus 2 in the denominator. Well, that's 1 over 0, that's undefined. I can't plug undefined into my function f, so this has no answer. Alright, so this illustrates an issue with these compositions of functions. Along the way, throughout the whole process, we need to be plugging stuff into functions that can actually go into those functions. So I wasn't supposed to plug negative 2 into this function because negative 2 is not in the domain, right? If x is negative 2, then we break h of x. Well, if we break h of x, then we can't exactly plug the result into f. So that should be undefined. Now, if we look at the composition function we found, f composed with h of x, in the previous example we've simplified that down to x plus 5 over x plus 2. Alright, so if we try plugging negative 2 into this, you'll see we run into a similar problem. Negative 2 plus 5, that's fine, divided by negative 2 plus 2. Here we end up with 3 over 0, which is again undefined. So this goes back to a subtle little piece of information associated with that definition. Review that in the notes. It is a subtle little thing, but f composed with g of x is what we get when we plug g of x into the function f, and the domain of this is going to include all x in the domain of g, such that g of x is in the domain of the outer function. In other words, if I plug something in that I'm not allowed to plug into g, we run into trouble, as we saw in this previous example. I could also try to plug something into f that would be a problem, and let me show you what I mean by that. So here we have two new functions, f and g, f of x being 1 over x and g of x being 2x minus 4. So f composed with g of x, that is, we want to find f of g of x. So we want to plug g of x into the function f. So f of 2x minus 4 would be, well, what does f do? It plugs the input into the denominator, 1 over the input. Okay. So that's our composition. What is the domain of this function that we've found? Well, we want to make sure that 2x minus 4 is never 0. In other words, 2x can never be 4, so x itself can never be 2. Okay. So, going back and looking at the process, the outer function has issues with its domain. G of x is all real numbers, right? We can plug anything we want into this inner function. But the domain of f is not all real numbers. Negative infinity to 0 and 0 to infinity, right? We can't divide by 0. So what we need to think about is what x values make g of x be 0. And that's what where we're coming up with x cannot be 2. So the domain of the inner function is all real numbers. We can plug anything into that. But we run the risk of making g be 0, making the denominator of our final function be 0. And that happens when we plug 2 into the composition function. So the domain of f composed with g is negative infinity to positive 2 union 2 to infinity. So the way I like to handle these is leave them till the end and look at your final function and think about what's happening with the x values. You're plugging your x value into the inner function. Is that allowed for the x values that you're interested in? What kinds of results do you get? So there we have to ask about range. What's the range of this function? Because those y values are now going to become, or I shouldn't say y values, those outputs are now going to be used as inputs into the outer function, into f. So domain can get a little bit tricky with these, but it's easy to follow if you're comfortable with how these compositions work, what they do. So let's look at a couple more examples where we aren't necessarily able to find the composition function. So in our next example, we don't have formulas for either of our functions. Instead, we have graphs. So in this case, one option would be to derive the formulas, figure out what the equation for each function is, then compose one function with the other, then plug one, in the first case, into the result. I would argue that's quite a bit of work, and we can avoid it by thinking of the definition. So f composed with g of 1, what's that asking for? It's asking us to take 1 and plug it into g, calculate the result, and plug the result into f, and calculate the result of that. Now, if we view it in this way, we can very easily tell that we need to know what g of 1 is. Alright, now our g is our line here. So g of 1, if we look on the graph, we're looking for the x value of 1. What is the result? What is the y value associated with that? Well, g is 0 when x equals 1. Okay? So, now all that we need to find is f of 0. And looking at the graph of 0, our curvier graph here, when x equals 0, so now our input becomes 0, the output is 0, right? We're looking at the point 0, 0. In similar fashion, we can evaluate g of f of 4. Let's see how that goes. So g of f of 4. We'll take f of 4 off to the side. And think about our graph. Now we're looking at the f curve. F of 4, if we come over to 1, 2, 3, 4, f is at a height of 2. So we'll plug that back in. This is g of 2. Now if we look on the graph of g, switching to the linear graph, if we come over to 2 and come up to our graph, we're at a height of 3. So without even knowing what this function is, simply by knowing what it's supposed to do, we're able to use that theory to evaluate that function at the value of 4. Now here's a little bit of a weird one, g of 2. Well, what's that asking? It's asking for us to plug g of 2 into g again. In other words, we're going to plug 2 into g, figure out what that is, and plug that into g again. So g of 2, let's take that off to the side. Now again, we're looking along the curved graph, or the linear graph, coming over to 2, coming up to the graph. That's at a height of 3. So that's going to become our input. So g of 3. Now I need to think of 3 as my input, come along the x-axis to 3, come up to my linear graph, and the output should be 6. So this is a real test of your comfort with the idea of the inputs and the outputs, and it's very important to keep those ideas straight. Whether something is x or y depends on whether it's an input or an output. And whenever we're inside function parentheses like this, here we see parentheses around a 1, around 4, around 2, around g of 2, then whatever's inside those parentheses is an input, and we need to know what that input is, otherwise we can't do anything with it. So, calculate what the input is, and you'll be able to figure out what that input does. Okay, so you should have all of the tools necessary to tackle the problems out of this homework set. Go ahead and take a look at those and bring any questions you have to class.